Today, we tackle a problem that challenges us to find the minimum time to visit a sequence of points on a 2D plane. You can move horizontally, vertically, or diagonally. How do we ensure we always take the fastest path between each consecutive point? Given an array of points, where each point is represented by its x and y coordinates, our goal is to find the minimum time to visit all points in the order they are given. We can move 1 unit horizontally, 1 unit vertically, or 1 unit diagonally in 1 second. The core challenge is to correctly calculate the minimum time between any two adjacent points. A naive approach might involve trying to simulate moves, but that quickly becomes overly complex and inefficient. There's no obvious brute force path that enumerates all possible paths between points. Any approach that doesn't leverage the specific move constraints directly would likely involve redundant calculations or unnecessary state tracking. The problem's constraints hint at a more direct mathematical solution rather than iterative pathfinding. We need a way to instantly compute the minimum time, not search for it. Complexity would easily exceed big O of n if we weren't careful. The key insight here is understanding the allowed moves. Moving 1 unit diagonally covers 1 unit horizontally and 1 unit vertically simultaneously. This means to get from point A to point B, we can always maximize diagonal moves until either the horizontal or vertical distance is covered. The remaining distance will then be purely horizontal or vertical. Therefore, the minimum time to travel between 2 points is simply the maximum of the absolute difference in their x-coordinates and the absolute difference in their y-coordinates. This is known as the Chebyshev distance. Our algorithm iterates through the points, calculating this Chebyshev distance between each adjacent pair and summing them up. We compute the absolute difference in x, then the absolute difference in y, and take the maximum of these two values to add to our total time. Let's trace this with our example. Points at 1, 1, 3, 4, and -1, 0. We initialize total time to 0. First, we consider moving from 1, 1 to 3, 4. The absolute difference in x is the absolute value of 3 minus 1, which is 2. The absolute difference in y is the absolute value of 4 minus 1, which is 3. The maximum of 2 and 3 is 3. So we add 3 to our total time. Now, total time is 3. Next, we move from 3, 4 to -1, 0. The absolute difference in x is the absolute value of -1 minus 3, which is 4. The absolute difference in y is the absolute value of 0 minus 4, which is 4. The maximum of 4 and 4 is 4. We add 4 to our total time. Total time becomes 3 plus 4, which is 7. We have processed all pairs, and 7 is our final answer. The final result for the example is 7. This is correct because we've applied the Chebyshev distance formula between each consecutive pair, ensuring we always take the most efficient path segment by segment. You'll spot this pattern when a problem involves grid traversal with diagonal moves, and the cost of a diagonal move is the same as a cardinal move. Look for scenarios where minimum time, or minimum steps on a grid, can be simplified by a direct distance metric, rather than complex pathfinding algorithms. This often points to a mathematical distance formula. The time complexity is O of n, as we iterate through the points array once. The space complexity is O of 1, as we use only a few constant extra variables. Try applying this Chebyshev distance pattern to other grid-based problems. It's a common optimization. If this helped, hit like and subscribe for more efficient DSA solutions.